Good morning, everyone joining our conference today. I want to welcome the NISS Graduate Student Network Research Conference. This is the third annual Graduate Student Research Conference, which has been sponsored by NISS's affiliate, Procter & Gamble. I'm Jim Rosenberger, Director of the National Institute of Statistical Sciences. I'm thrilled to welcome you to this two-day conference. We host this for the benefit of our affiliates, for graduate students, those participating as speakers and as attendees. And I want to thank the organizing committee of the Graduate Student Network, who are listed on the website and are chairing the sessions today and tomorrow. Special recognition is owed to Piamu Liu, chair of the steering committee, and Megan Glenn, our NISS staff member who is hosting our Zoom meeting today. She's on the screen as we speak. This annual conference has been sponsored since the beginning, since the inaugural event by Procter & Gamble. And to open the conference today, we've asked Matt Barker to give us a brief introduction to P&G and share his role in the organization. Matt is a research fellow in data science and statistics in P&G's Data and Modeling Sciences organization. So with that, without further ado, Matt, I will turn this over to you.
Thanks so much, Jim. Can you hear me okay?
Yes.
All right. Yeah, as Jim said, I'm Matt Barker. I'm a statistician and data scientist at P&G, going on 23 years now. And P&G is a multinational corporation that is one of the world's leading manufacturers of consumer goods. It was founded in 1837 and headquartered in Cincinnati, Ohio. And P&G has a wide range of products, including beauty, grooming, healthcare, fabric and home care, and baby and femme. And our products span different markets, including including brands you may know, like Tide and Crest, Gillette, Pampers, Pantene, and we have operations in about 70 countries, products sold in over 180 countries. And P&G's impact on global consumer goods sector is really significant. And we're known for our commitment to innovation, high quality products, and corporate responsibility, often leveraging advanced technologies like data science, the statistical sciences that you'll talk about today, and AI to drive business growth and even sustainability goals. And we're really proud of 51% of our 7,000 R&D employees worldwide are women. And we're honored to be recognized as #1 by the US Patent and Trade Office with the highest rate of women innovators. And this is really no accident. We believe in inclusion, and it really starts with all of us. So my time is brief here, but because we want to get to these amazing innovative talks that you guys are going to give. And so I just want to share a few websites with you in the chat that includes some background about P&G, our community impact, and a few different blogs, including P&G careers and data science information. So with that, thank you for the opportunity to sponsor this 2023 NISS Graduate Student Research Conference. Thank you.
Thank you, Matt, for your welcome, and especially thank you and your company for sponsoring this research conference. Please convey that to your leadership. And with this, I want to turn this over to first Megan to show the day's schedule, and then we'll turn it to Rebecca Kurtz-Garcia from UC Riverside, who is going to be the chair of the first session. Megan, do you want to share your screen?
Sure. Give me one moment. All right. So here's, oh, yeah, I'm not muted. All right. So here is the agenda for today. We're going to have our first session with the Bayesian methodologies and causal inference. And we have 4 presentations for the graduate student presentations. And then afterwards, we'll take a quick break. And then we have the first keynote speech from Daniel Jeske. And then also we have a short course on scientific writing that will be from Donald Richards. All right, so with that, I will let Rebecca take it away and introduce your first presentation.
Hi, everyone. Welcome to the first section. We're going to be doing Bayesian methodologies and causal inference. We have 4 presenters. Each presenter has about 20 minutes. The objective of the time is to do about 15 minutes of your presentation, about 5 minutes for questions and transition. For this section, if you get to the 18-minute mark and you're still doing your presentation, I'm going to go ahead and change my Zoom background to red. So you get a hint that time is running out. And if we're going over 20 minutes, then I'll begin to interrupt so we can start with the next presenter. Please have your presentation slides ready. So we'll go ahead and get started. The first person is Ouyao Lin. And for anyone in my section, I apologize if I mispronounce names. Please let me know afterwards. But we have Ouyao Lin from UC-Berkeley. So without further ado.
Okay, thank you for the introduction. So let me share my screen. Okay, I think just a second, I have to hide this one. Okay. Okay, so I think I can begin. So I'm Zhexiao Lin. I'm now a PhD student in statistics at UC Berkeley. So in today's presentation, I will discuss about regression-adjusted imputation estimators of the average treatment effect. So I will first so this presentation is based on 2 papers. The first one is estimation based on nearest neighbor matching from density ratio to average treatment effect, and this paper is together with my 2 fantastic advisors, Peng Ding at UC Berkeley and Fang Han at UW. And this paper is now conditionally accepted at Econometrica. And the second paper is on regression-adjusted imputation estimators of the average treatment effect, which is the title of this presentation. And this one is with my advisor, Fang Han. It's now in submission. So I will first introduce, I will first introduce a general big picture. So we consider a very general case study case, and we have several units, and for each unit we can use 3 features to describe each unit. So for each unit we have yi1 and yi0, which is the 2 potential outcome, because we consider the potential outcome framework. And also for each unit we have some covariates xi to describe this unit. Then it is a very ideal case because we cannot observe these 3 features, yi1, yi0, and xi simultaneously. What we have in practice is 2 groups, the treatment group and the control group. For the unit in the treatment group, we can only observe its potential outcome on the treatment. And for the unit in the control group, we can only observe its outcome on the control. So we cannot observe yi1 and yi0 simultaneously, and we'll use D for the indicator of whether this unit is from treatment or the control. We use D equal to 1 for the treatment group and D equal to 0 for the control group. And also we'll use the red color for the treatment group and blue color for the control group. Our goal is to estimate the average treatment effect, which is the expectation of the difference of the 2 potential outcomes based on the observed data, yi, xi, and di. So we can use this average treatment effect to evaluate the effect of this treatment. So a very, I would say a very natural idea to estimate the average treatment effect is to impute the y1 and y0. For the unit in the treatment group, we can simply use its observed outcome to be the potential outcome on the treatment, because this unit is on the treatment. But for its counterfactual outcome under control, we cannot observe it. So we'll use the information we have to estimate it. A very natural idea is to use the information from the opposite group, because the opposite group is the control group. So we'll use a kind of weighted mean of the outcome of all the units from the control group. So for example, we can take this unit to be unit J and this unit to be unit I, and we have a weight Wj to I for the contribution of estimating Yi0 using Yj. Okay, we can construct all such weights for all the units in the control group, and it can incorporate many different kinds of matching methods. We can incorporate the kernel matching, weighted nearest neighbor matching, local linear matching, and also honest random forest. All these matching methods can be called the local matching, because we'll give larger weights for some units and smaller weights for some other units, which are very far away from this unit. I use this weighted version of the outcome, but in practice we may incorporate an outcome model. So the reason for using the outcome model is that we want to do bias correction. If we do not do bias correction, there will be a large bias asymptotically. So the outcome model is defined as the conditional mean of the outcome given covariates. So we will use mu1x and mu0x, and we can use some non-parametric regression techniques to estimate these two outcome models, and we denote these estimators by mu1 hat and mu0 hat. And then the regression adjusted imputation estimator can be modified in this way. So in previous, we do not have these mu0 hats and mu1 hats. In the regression adjusted, we incorporate these two estimated potential outcome, these two estimated outcome models, and then the final average treatment effect estimator will be defined in this way after we estimating the two potential outcomes. So it is a very simple sample mean, the difference of the two potential outcomes. Then we will have several observations for this estimator. So this estimator has some very fantastic properties. The first one is that this regression adjusted local matching average treatment effect estimator is doubly robust. So I will explain what is doubly robust, and this decomposition is very useful for prove this property. So we'll first assume some standard data assumption. So this one is the overlapping assumption and the unconfounding assumption, which is very natural in causal inference literature. And also we have some weight assumption. This weight assumption can be satisfied for many different kinds of local matching method, including all I just said, like kernel matching or locally matching or like nearest neighbor matching. And then we'll have two assumptions. The first one is the density assumption, and the second one is the outcome assumption. So the double robustness said that as long as one of these two assumptions holds, then the final average treatment effect estimator will be consistent. So we only need one of them to be true. So the first one said that we allow the misspecification of the outcome model, but we need this key identity to be true. The outcome assumption said that we need the outcome model to be correctly specified, because this is arbitrary mu bar, but this one is the true the true outcome model. And then we can just give a very mild condition on the weight. So the double robustness is one of the property we have. Also, we prove that the regression adjusted local matching is semi-parametrically efficient. So this decomposition is also very useful for our proof, but I think I can skip these proof techniques and we'll come to the final conclusion. So the semi-parametric efficiency says that this average treatment effect estimator is root n consistent and the asymptotic variance reaches the semi-parametric efficiency lower bound. So the semi-parametric efficiency lower bound said that for a class of regular estimators, this is the lowest variance we can achieve. So we'll say this estimator, this average treatment effect estimator is optimal in some sense. So we still need some assumptions, but the key assumption is the smoothness of the outcome model, and also some smoothness on the density model. Actually, this assumption can be verified for, I would say, for different cases, and we will verify this case by case. I think maybe the most important application for our general framework is the nearest neighbor matching, because nearest neighbor matching is commonly used in practice, and actually the theory of the nearest neighbor matching is very sparse. But I will say the real data example, if we apply the nearest neighbor matching on real data, the results will be very good. So for the nearest neighbor matching, I will explain what is nearest neighbor matching. So for this unit in the treatment group, we can construct the weight in this way. We find the nearest neighbor of these red units in the blue units. So for this unit xi, we'll find if we want to find 3 nearest neighbors, then we'll find the 3 closest one in the control group. So we can see these 3 blue ones are very close to this red one, but this blue one is very far away from this red one. So we'll give these 3 blue ones the weight 1/3, and all the other blue ones the weight 0. And then we need to verify this key identity, which is essential for the double robustness holds or the semi-parametric efficiency holds. So I will first provide some intuition on why this identity holds, because the proof technique is very subtle. So the intuition is that we can regard this identity to be the density ratio of the covariance distribution under treatment versus the covariance distribution under control. So we can regard control group and treatment group separately, and we want to estimate the distribution of the covariance for these 2 groups. And then this one is the number of time each unit to be matched. And I will explain what is this identity, what is this quantity. So for example, we still focus on this red one, and to calculate this identity, this quantity, we find the nearest neighbor of all the blue units. So for this blue unit, we find 3 nearest neighbors, and then this red one, this red one, and this red one will be the 3 nearest neighbors. In our first paper, we prove the double robustness and the semi-parametric efficiency for the nearest neighbor matching, and also we generalize this framework to the local matching, including kernel matching, witness and neighbor matching, local linear matching, honest random forest in our second paper. And we made a conjecture that any consistent regression-based imputation gives rise to a semi-parametric equally efficient average treatment effect estimator, as long as we assume some very mild conditions on the imputation. But of course, the proof is very difficult, and we can only like push our results to these several maybe very simple or easy to analyze a method for non-parametric regression. I think that's all my presentation. Thank you.
Awesome. Thank you so much. I did have a question on slide 9.
Mm-hmm. This one?
Yeah, you have these 2 different assumptions for EE robustness.
Yep.
Do they have like natural interpretations of like what they like, because they look technical. Like, do you have like a quick, this is that, this is this type of interpretation for them?
Yes, actually, this one can be related to the AIPW. So for the AIPW, we have the propensity score estimator and the outcome model estimators. And then the double robustness of the AIPW said that as long as one of the estimator is consistent, then the final average treatment effect estimator is consistent. So it is very similar to our case because this one corresponds to the propensity score consistency, because this one is very, you can see it is very similar to the propensity score as long as we plus 1 for this identity. So this is the propensity score. So we'll say the local matching can intrinsically estimating the propensity score, but we do not have to construct a propensity score estimator explicitly. And this one is the outcome, the consistency of the outcome model. So this is, yeah, some natural.
Thank you.
Thank you for the question.
Do we have any other questions? I think we could do one more because we started this one a little late. Okay, well, you can still ask questions towards the end of the session if we have time. But thank you so much. That was an awesome presentation. I love the pictures.
Thank you.
It's really cool. We have another presentation from Runjia from the University of Pittsburgh. So again, go ahead and take it away.
Okay, so hello everyone, and my name is Runjia Li, and I'm a third-year PhD student at the University of Pittsburgh. And today I'll be presenting my work on doubly robust estimation of conditional average treatment effects for time to event outcomes with competing risks. And this is work advised by Dr. Joyce Zhang. And this is my outline. And before jumping into the proposed methods, I will first introduce some related context and our motivation. So let's start with a motivating example, a real-world problem from our medical center. So here in this figure, the sepsis patients in 3 colors represents patients with different characteristics. The treatment glucocorticoids here are widely used in sepsis patients, may decrease the time to shock reversal, and shock reversal is a kind of recovery as our main event. But it may also increase the adverse events such as the immunosuppression or secondary infection, which is our competing event. And the competing event can prevent the occurrence of the main event. And so this is the competing risk settings. And to help pinpoint the high benefit patients and reduce the use in patients unlikely to benefit, making a better treatment strategy, we need to understand the heterogeneous treatment effects in patients with different characteristics on the time to event outcome with competing risks. And to provide some context, the competing risks analysis refers to a special type of survival analysis, and that aims to correctly estimate the marginal probability of an event in the presence of the competing events, when there are more than one cause of failure. and the occurrence of the competing event may affect the occurrence of the main event. And here are some widely used methods. We prefer to use the fine-grained subdistribution here because it can provide us a direct relationship between covariates and cumulative incidence, which we will introduce more in our methods section. And this is often used in clinical prognosis and prediction. And hazard ratios, which are widely used from those models, does not provide a causal interpretation. And the case, I want to introduce the definition of the conditional average treatment effect Tate. It is defined as the expectation of the difference between the potential outcome given the covariate. And the potential outcome here, as also introduced by Zhexiao earlier, it is the outcome that if the subject's treatment had been assigned to a treatment level A, which is possibly contrary to the fact. And the Z here represents the baseline covariates. Obtaining the Tate can help us capture the heterogeneity of the treatment effect and allow more precise and targeted treatment strategies. There are already some approaches for estimating causal treatment effects, and some of them are outcome-based, including the regression and machine learning-based models, and treatment-based, such as propensity score-based methods, and also the doubly robust model methods that modeling for both, including targeted maximum likelihood estimation and the AIPW and doubly robust learner. And doubly robust here means that, and also Zhexiao has introduced that if either one of the outcome-based or treatment-based mechanism is correctly specified, then the estimate would be consistent. And if both of them are correctly specified, then the estimate is efficient. So this is a very good feature. And the gap is that current methods with DR feature fail to address the variation in treatment effect, especially for the when the estimating the Tate in a time to even outcome with competing risks. So our objective is to propose a new causal quantity for time to even outcomes with competing risks, and to develop a framework for estimating Tate that target on the cumulative incidence function and have the doubly robust feature and being flexible to incorporate various algorithms. And then I will dive into some details on how to reach these goals. First, let me describe the settings and notations. We have the observed time to even data with competing risks, and we have the right censored time, event time X, the event type indicator theta, and the binary treatment strategy A. And for competing risk settings, the cumulative incidence function, as defined here, is always the interest of researchers and the physicians, because it is defined as the probability of the occurrence of the main event before a time 0. And this is useful because for making prediction and making the treatment decision, because as we mentioned in the introduction part, it can directly reflect the relationship between fine-grained model it directly reflect the relationship between the CIF and the covariate, making it more interpretable. And here we define the Tate using the transformed CIF, the C log CIF. And we could also use F to define this quantity, but for the purpose of better demonstrating our results and distinguish the predictive and prognostic factors, we use the transformed one. And they deliver same information because it's a monotonically increasing function of CIF. And the TA here is the counterfactual failure time that one would be observed if the subject's treatment set to A. And so the parameter that can be causally identified from the observed data within the potential outcome framework by Rosenbaum and Rubin. And so the task is now reduced to estimating the statistical parameter. And our proposed method is based on the idea from TMLE, the targeted maximum likelihood estimation that proposed by van der Laan and Rubin in 2006. It's a semi-parametric estimation framework and provides general methodology for estimating the causal parameters. And TMLE framework allows the use of machine learning models, it will still have the valid scenarios for statistical inference, which is a very good property. And most importantly, it has the doubly robust feature. And you may wonder how this is realized. It's actually just a two-step procedure. And this figure just provide a big picture on how it works. And we will also see it in our next slide. So first, based on the observed data, we will construct an initial estimator for the probability distribution. And then in the second step, it's a key step. In the targeting step, we update the estimator to a P star, such that the targeted estimator P star solves the efficient influence curve equation. And when it is solved, the targeted estimator has the asymptotic linearity with the smallest possible asymptotic variance. And the key to solve this equation is to find a parametric submodel such that the score function is equal to the efficient influence curve function phi. And when the epsilon in the submodel reach 0, the score function is also 0, and then is the EIF is 0. And based on that, this is our proposed framework. So we first stratify the data based on a fixed group of covariates, and then within each stratum, we generate initial estimate for the CAIF and the propensity score. And this can be obtained by various algorithms or models. And then in the second step, we update the initial estimates using the sum model. Here is the logistic regression model. And the clever covariate H is obtained from the first initial estimate step and will also be updated within each iteration. And then in this logistic regression, we obtain the estimate epsilon, the coefficient epsilon. And then we also have the estimate, CAF, and we plug them in and update the outcome, the outcome CAF K+1. And so that within each, using these iterations, we will iterate it until we get a very small epsilon, which is close to 0. And then we calculate the stratum specific ATE as our kit. And next, we run simulations to demonstrate the doubly robust feature and flexibility of our method. Here is our simulation setup. We included 4 covariates to represent the patient's baseline characteristics. And the treatment A follows a Bernoulli distribution, meaning this is an observational study here. And our main event time is generated from a unit exponential mixture. And to show the doubly robustness, we had 4 scenarios where the outcome model and propensity score model were correctly specified or misspecified. Correctly specified means that we include all covariates, and misspecified means that we only include Z1, Z3, and Z4. And we compare with S-learner and T-learner. Those are widely used methods for estimating Kate. And we incorporating various algorithms, and we calculate the Bayesian RMSE for performance evaluation. So here is the result. It shows the Bayesian RMSE of K estimations from different algorithms and scenarios. In first scenario, the best situation that both model are correctly specified, we could see that the bias and RMSE are all low for all algorithms. But for scenario 2, when the outcome model is misspecified, we could see that the ST learner will have the inflated bias and higher RMSE, while our methods also still have low bias and RMSE, a similar level as in scenario 1. And using the Lasso penalized fine-grained regression for initial estimates of CIF gave us the best performance. And similarly, in scenario 3, when the propensity score model is misspecified, we still have a relatively low bias compared to ST learner with model specified. And even in scenario 4, the worst case, the TMLE has similar performance as T-learner when the outcome model is misspecified. And this violin plot directly shows the K estimates for all subgroups from different algorithms in scenario 2, where the outcome model is misspecified. And the red line shows the true K from our data generation, and the 4 panes represents 4 subgroups by Z1 and Z3. And the left pane here, we could see that the true K is that there's no treatment effect while the outcome model is, when the outcome model is misspecified, the ST learner may suggest that there are negative treatment effects, and which will lead to wrong treatment strategies, but our TMLE method still deliver this, the correct information. All right, so due to the limited time, I will have a quick summary of our work. So our proposed framework for estimating the K for time to event outcomes with competing risks has the doubly robust feature with protection against models misspecification and the flexibility of incorporating various algorithms. And it is consistent and stable across different settings. And in public health, it has more precise and targeted treatment strategies. And in the future, we will maybe demonstrate the proposed methods using data from sepsis patients in our medical center and explore more recent developed doubly robust methods and other algorithms. And here are the reference. And I would like to thank my advisor, Professor Zhang, for her expert advice and encouragement. And thanks for joining.
Awesome. Thank you.
Thank you.
Do we have any questions for Runjia? I had one for you. I saw that in your simulations, the sample sizes seemed like a few thousand. Is there like a rule of thumb for these models where it's like you should really be considering sample sizes of at least this big, or maybe the results aren't as strong? Like, is there a guideline for that?
Yeah, thank you for your question. So here, as I shown here, in the training data set, I include 3,000 for each one, and test data set, I include 10,000. I just wanted to have a good performance evaluation. So I include a lot in test data set and in training data set, because I also wanted to apply some machine learning algorithms. So especially because we have subgroups. So I'm hoping that we have enough sample for each group. So I have this number. But there's no, I think there's no rule of thumb. And I guess I just picked this number, which is similar to some literature that I reviewed before. And I think in the future, if the time is allowed, I can show more and compare some results using different sample size.
Thank you.
Thank you.
Before we go to our next speaker, I did want to check in about the recording situation. So I see Matt is our recorder. You probably don't want that role.
it's still recording, and I made Jim the co-host, so he also has the power, or should have the power. Yeah, where everything's working.
Okay.
I did have
be good.
Oh, go ahead, Jim.
I was just going to say, Megan lost her internet connectivity. We don't know why, but we're good. Keep on rolling.
Okay, we
Thanks.
should be good.
I
But
did
if we
have a quick question for the previous speaker,
of course.
just around implementation. How did you go about implementing your algorithm in order to test the simulations?
Oh, thank you. So we had 4 scenarios, and in each scenarios we used our methods and also some previous methods. And how we implement that, first in each training data set, I run our framework to estimate the Kate for each subgroup. And then I generate, actually I have an estimate for Kate for each stratum from each training set. And then in the test data set, there's only one. So in the test data set, we estimate the Kate for the test data set using the model that we have from each training data set. And then for this test data set, we calculate the bias and the RMSE. Does that answer your question? Sorry.
Well, and maybe so from a programming standpoint, how did you use a particular type of language to program this up?
Gotcha.
Did you construct a package so that others can reuse the algorithms you developed?
Oh yeah, I got it. So for this project I used R, and there are already some packages from Wonderland and Wonderland's students. Their lab, they have some R package for TMLE and also SuperLearner. But for mine, I think it is kind of special, because first is the Kate, and second is for competing risks. So I write the code by myself manually. So, and I'm hoping to wrap it up to a package so that it can be actually used in real world analysis. Yeah.
Got it. Thank you.
Thank you.
Runjia, I also have a quick question.
Yeah.
Just curious, on this slide, and there you mentioned there's 30% censoring. So I was wondering if there's any reason that 30% is chosen, or if that's not an important aspect of your research setup here.
Thanks, Tom. So regarding the 30 censoring, this is the number that I chose after discussion with my advisor, and we think this is a typical censoring rate that's being observed in clinical study and those cohort study. But she said that this might be a little bit lower than the truth, but we can adjust it later. Yeah.
Thank you.
Thank you.
Awesome. In the interest of time, we'll go ahead and move on to our next speaker. There is a 5-minute break in between this session and our keynote speaker. So if the speakers can hang out during that break for any extra questions. Our next speaker is Durbadal Ghosh from Florida State University. So please take it away, Durbadal.
My name is Durbadal Ghosh. I'm going to present modeling of clustered censored survival data with spatially correlated random effects using SBOT. I thank my advisors and my co-advisors for helping me with this research. So I start with the motivating data set. So we have a survival data, the survival response time to death of breast cancer patients in Florida. So our the response variable time to death is right-censored and clusters. The clusters here are the counties in Florida. We have other variables include the races and the stages of cancer. There are 2 races and 3 stages of cancer. We have 5 patient-level covariates. There is another variable called screening mammography or mammography screening. We do not have any patient-level information of that. Instead, we have a county-level information of SMU. So we do not know how many patients in a county are getting SMU, but we have an estimation of that from a survey called BRFSS. The main goal in our project is to know the effects of covariates on racial disparity and also how the survival function behaves based on different values of covariates. So what are the challenges in our data sets? First, our survival time is right-censored and it is clustered with variable cluster sizes. There is special association among the unobserved cluster effects, because remember the clusters are the counties in Florida. So also we have missingness in one of the county level covariate, which is SMU, and there is special association among the SMU values because SMU is a county level covariate. The existing methods include parametric and semi-parametric methods, for example, Cox's proportional model, but it is restrictive because it cannot deal with the interaction between time and covariate. Also, in our case, the functional form of the covariate is unknown. So we approach Bayesian non-parametric methods, particularly the tree-based methods. So Sparapany introduced a tree-based method for discrete survival time. Another notable paper is by Bosak, which can deal with clustered survival data using SBART. Their method outperforms other method, but the weakness is that their method cannot deal with the missingness or it cannot deal with the spatial association among the clusters. So to address the weakness, the innovations we do is that our model can handle continuous survival response. Our model is fully non-parametric and can handle the spatial association among the clusters, right? And our method can handle missingness and also can access the spatial correlation between the unobserved SMU. And computationally, our method is fast even for many clusters and when there are large cluster sizes. So before going to the model, I briefly review the Bayesian additive regression trees or BART. So why let's look at the standard regression setup. Y equals to bx plus epsilon, where epsilon is normally distributed, b is unknown regression function. B is basically the sum of decision trees G. So G has 2 parameters, tau k and mk. Tau k denotes the topology or the structure of the trees, while mk are the set of predictions associated with the terminal nodes of the kth tree. So bx is a piecewise constant function over the partitions of x. So here are 2 examples of regression trees. So the decision is of this form, that is x, there is a covariate is less than some cutoff, and the last node has this mu real number values associated with it, which is called leaps. So a decision tree basically partitions the covariate space, and it is constant in each of these partitions. So for example, if our covariate space is R2, then for this tree that is a single node, it is constant over the whole R2. If we divide the tree, if we split the tree based on the decision x1 less than 0.5, then we have 2 vertical halves. Again, if we further divide the tree, if we further divide the branch x1 greater than 0.5 based on the decision x2 less than 0.5, then we have 3 partitions, and the function is constant on each of these partitions. Now we define the prior distributions for each of the parameters. So firstly, the topology or the structure of the trees. For the structure of the tree, we have 3 things: whether we want to split at a point, which variable we want to split, and where to split, the cutoff point. So for the the tree tau k is non-terminal at depth d with this probability. The splitting variable is uniformly chosen from all the covariates. And the cutoff point is also uniform, AB, where A and B depends on the range of xj. And the leaves are independent in IID normal distribution. There already exist fast MCMC techniques using Bayesian backfitting to update the trees. So the idea there is that first they update the topology tau k given rest, and then update mk given tau k and rest. One drawback of BART is that it lacks smoothness. So SBART or soft BART introduces smoothness by taking probabilistic approach down the tree. SBART has lower variance and lower bias. So this is an illustration figure for the BART and SBART. So BART is piecewise constant on each of these partitions, while SBART is smooth on the boundaries. Now we look at conditional autoregressive model, or CAR. We do not know the patient level locations, but we know the county locations for each patient. So we have aerial data. The main idea here is that the neighboring counties should exhibit higher association than others. So the CAR model is basically phi I given the rest is normal with the weighted average of the phi's and the sigma square. Phi I is the cluster effect of county I, and Wij are the weights or the spatial distance between cluster I and cluster J. For our case, Wij is 1 if I and J are neighbors, otherwise 0. So in our case, it is basically the weighted average of the neighbors. Some standard notations: I stand for clusters, J stands for the patients within the clusters. We have Tij, the survival time, censoring time is Cij. We have observed right censored Yij. Delta Ij is the censoring indicator. We have covariates, the full data, and the survival function is probability T greater than T. We have hazard function, which is F, the density divided by the survival. And we have the cumulative hazard, which is integration of the hazard. First, we deal with the missingness of the SMU. So the true SMU is unknown, but they have spatial association. So our model is this. SI follows binomial Ni Qi, where Qi is the true proportion, SMU proportion for county I, and SI is the number of observed patients with SM in the survey. And we give the prior for Qs to be CAR because they are spatially associated. And we need to take a logic transformation because Q is a number between 0 and 1. Then we augment Qi in cluster I with the posterior estimate of Qi. And we use that value as a covariate in our survival model. Now we have the survival model. We model the hazard function. So we have a baseline hazard. We have the random effects due to cluster. Wi are the random effects due to cluster. Phi is the CDF of standard normal distribution. B is the BART function. So B is a function of T and X, which means it can take care of the interaction between time and covariate and also within covariate interactions. We take the baseline hazard to be constant and the prior for W's CAR to be CAR. And we need to take a log transformation because W is a positive random variable. And the prior for B is BART. So the density is basically hazard times the survival. So the likelihood contribution for the patient Ij is hazard to the power censoring indicator times the survival. So our hierarchical model is this. So we have the hyperparameters, which are a priori independent, and we take the priors to be non-informative or weakly informative. And the prior for B is BART, W is CAR. And this is our likelihood contribution. If we look into the likelihood, we see that the function B is inside this integration, which makes the posterior of B analytically intractable. So it's hard to update the function B. So the idea here is to use data augmentation. So suppose we want to sample theta from F theta given D, then if we can find an M, a random variable M, such that sampling theta from the joint from the distribution theta given M and D, and M from the distribution M given theta and D are straightforward, then we can sample theta from this distribution using Gibbs sampling. So basically we sample M from this distribution and then sample theta, and we iterate this. So I only show the data augmentation scheme for no censoring case, because for the censoring case, it is very similar. So this is the standard regression setup, right? So if we look into the posterior, so the function B, so the B comes inside the, comes inside as a mean of the normal distribution. So phi is the PDF for normal distribution, and B comes as a mean of this. So if our targeted posterior is this, so if we can get a posterior which looks like this, then we can use standard techniques to update the function B. So we do 2 levels of data augmentation for each patient IJ, GIJs and ZIJs. So we define the conditional distribution of ZIJs is non-homogeneous Poisson process with this intensity function. Note that G is a vector. So the distribution of G's is this, and the distribution of T given other parameters is this. So this is the likelihood. So this is the distribution of T. Now, if we multiply this to terms, we get the joint of G and T. If we look into the joint, we see that the function B is now outside the integration, which is good. But we have still not got our targeted posterior distribution. So we need to do another level of data augmentation, which is Z. So Z follows truncated normal. Now, if we calculate the joint of G, Z, and T, it turns out to be this. So the function B only appears as a mean of the normal, which is exactly the case we wanted. So now we can use standard techniques to update the B. So this is the hierarchical specification of the model with the augmented data. So now we use Gibbs sampling to update all the parameters. So basically we generate G's from non-homogeneous Poisson process, we generate Z's from the truncated normal, and then we update other parameters from their full conditional distributions. So what are the innovations in computation? So we use data augmentation to do Gibbs sampling. We have 67 counties, so it's a high dimensional setup. So we use Hamiltonian Monte Carlo to update the frailty, the W's, instead of MH. We use RStat interface, and we use the package softbot by Dr. Linero to update SBot, and our computation is fast. For the data analysis, here is the setup for the data analysis. We have counties, we have 2 races, African American and American whites. We have 3 stages of cancer. These are the biological covariates, and the last 3 are the intervenable covariates. We do a stratified analysis for each stage race combination. There are 3 stages and 2 races. So we have 6 strata. Among all, we have checked other residual plots, for example, Deviance residual, Martingale residual. I only saw the Coxland residual plot. So the green curve is our method, and the red curve is the method by Bossachs. And our method is closer to the reference line, the black line. So our method performs better than the Bossachs method. We also calculate the importance of covariates for each stage race combination. So how do we measure the importance of covariate? So we count the number of times each covariate appears in all the trees, in all the iterations, right? And then we sort of we scale that to 0 and 1. So these 3 are the intervenable covariates, and these 4 are the biological covariate. For the African American group, the intervenable covariate turns out to be more important. Just to be clear, the green one is the highest number, and the second highest number is the red one. So for the African American group, the intervenable covariates turn out to be more important, while for the white American, it is the biological covariates that turns out to be more important. We also estimate the survival functions. Under this setup, we fix the stage distance, median SMU, tumor grade to be 3, and vary the other covariates. So this is the estimation of the survival function. So for the group, African American group, and this is the estimation of the survival function for the American whites. So, and this is for a county. I believe it is for, this is for a particular county. So for every county, we have this curves, right? So I think this is the Miami County. So we observe the same pattern. So basically, we observed that for the African American group, for the first few years, the survival curves dips quite quickly than the whites, which means there actually is racial disparity between between the two races. We also calculate the expected number of years saved if we close the disparity between the two races. Just we can do this just by taking the integration, and we also the future works are that we are trying to access the causal effects of the intervenable covariate on the survival, and we are also trying to access the causal effect using tree-based method like BART. And this concludes my presentation. Thank you.
Awesome. Thank you so much. If we have a very quick question, we can try to squeeze it in.
In the chat, we just had a question about clarifying what SMU means, what it stands for.
SMU stands for screening mammography. So
Okay.
it's whether we screen whether a person gets screened or not screened. That variable is basically denotes the screening mammography. So basically, we do not have the patient level information whether a person gets screened or not screened, but we have sort of a number of people in a county getting screened, or the proportion of people getting screened for a county.
Awesome. I see, Samuel, you'll also have your unmuted.
Yeah, I
have a quick question.
One quick question. So you mentioned that the so thanks for the talk. You mentioned that the data augmentation when you're sampling from this, it's fast. Do you have can you give us a sense of like what do you mean by fast, and for your particular kind of problem of context, what computation time might look like?
Yeah. So it is because we have two steps, right? One is the data augmentation to update the BART, and also the spatial to update the frailty. We have to use the Hamiltonian Monte Carlo. So so I think for an iteration of 10,000, it took almost like 1.5 days with all the steps together, which is actually fast because with our data set has almost 76K patients. So with this large data set, I compared with the Bossak's computation time. So it's similar to them. It's a little more higher than that because we are also incorporating the spatial thing into it. So, but yeah, so it's actually quite fast, I would say.
And then we have one last question in the chat, and we will move to our next presenter. Is SMU categorical?
SMU is so the data we have is a number. So it's how many patients is an estimation of the number. But after we transform that SMU to a number between 0 and 1, we take the proportion between 0 and 1. So let me quickly share the screen once again. I will go to this page. So the observed SI is the observed number of patients with SM in BRFSS. This is the observed data, and this is the data we augment. This is the augmented data. QI is the augmented data. This QI is a proportion. So this is a number of observed patients with SM, and this is a proportion.
Awesome.
Is that clear?
I think so. I hope so. But if we have more questions, please ask during a break later in the conference. But we're going to go ahead and move to our last presenter, Ghui. If you're ready, take it away.
Okay, thank you. Okay, so hello everyone. So my name is Gehui, and I come from the University of Pittsburgh, and I'm a PhD student in biostatistics. And today I'm going to talk about my work about the Bayesian inference on stochastic volatility model with informative missiness. And this work is advised by Dr. Robert T. Crafty. And so here's the overview of my talk today. So as the technology evolves now, the mobile device can now collect like activity and emotional data in people's natural environment. And among this kind of data, the EMA data is actually one very important example. And our motivation study, the daily emotions and relationship study, also collects this EMA data. It collects data from young adults who were recently released from the inpatient facility after suicide attempt. And these participants are given a cell phone-based application, and they were asked to self-report the measure of affect and mood 7 times per day. And here's a small example from the data. It's a measure of happiness over time from one of the subject in the study. So you can say 2 to 21 days of observations, and the variation in the measure of happiness is huge, and there are some missiness there. So the past research has already found an association between the variability in the mood and the clinical outcomes. And we think the stochastic volatility model could be potentially an interpretable metric for EMA data. So comparing to the common approach that use summary statistics over time, the stochastic volatility model actually directly model the variance series as a dynamic stochastic process. So it can provide a more comprehensive picture of the variability in the data. However, the observational nature of the mobile device collected data could result in some non-ignorable missiness. But this stochastic volatility models, they're kind of derived from in the financial world, where the missing not random is not they're not considered in this structure. So existing methods are not account for this MNAR structure. So for example, the commonly used ad hoc methods, they simply ignore the missing part, just combine all the observed data, if they're continuous. And this method, assuming the missing complete at random. And so Kim-Stouffer proposed a method to handle the irregular sampling. It assumes MAR, missing at random. So in terms of how to deal with missing not at random, there are two very popular methods. So the first one is a selection model, where you directly model the missing part as a function of the observed part. Another is pattern matcher model, where you assume the missiness are decided from a series of latent patterns. However, both methods actually involve some unidentifiable issue, and that can be propagated in all the components in this decomposition. So to address this problem, Tukey proposed an alternative method to decompose the joint distribution, which, unlike all components there, will be accessible. This representation is revisited in 2020 by Franks, and they demonstrate that it's tractable when the data are independent and the distribution is in the exponential family. In our case, the stochastic volatility model have a sequential Markovian structure, so it allows us to actually model the missing mechanism and extend this to case representation. So now I'm going to share the definition for the univariate stochastic volatility model. So YT here is the real value of the observed time series, and the HT is the latent stochastic process, which is the volatility process. And so I'm going to define the response indicator here. So RT will equal to 1 if we observe YT. We do have a couple of assumptions about this messiness. So we assume that Y1 is observed, and also the RT only depends on the whole series through YT itself. So the last one is the RT series themselves are independent if we're conditional on the YT series. We consider a scenario where we can actually model the conditional logouts of the missing, like RT equal to 0, as a known function of YT. So for our talk today, we consider a simple case where we use a simple logistic regression. So it actually comes from our motivation study where we have assumption that if we have like higher level of negative effect, it's more likely to have messiness in the data. So in order to develop our imputation method and also the Gibbs sampler, we first did a likelihood decomposition. So we decompose this joint likelihood of Y0, which is missing site, and H1 to N, the volatility process, and given the Y1, which is the observed site, and all the parameters. So we follow the Markovian structure from this model, and we did some linear algebra, and so it can finally be decomposed into 3 parts. So the first part is, you can say like a warm up or initial state, so for H1. And the second part is when we observe YT. So it's actually the same as if we don't have any missiness in the data, so we can use available partial Gibbs method to estimate HT. The third part is if we don't observe YT. So in this case, because this, like you see, this distribution involved in YT, we have to first do imputation based on this part and account for that. We like use modified method to estimate HT. So given the decomposition, we propose this Gibbs sampler, which has 2 steps. The first step is to sample all the parameters given the whole series. And the second step is to sample the Y0 and H series. So our imputation method is based on the 2-case representation. So from that, we can represent the conditional distribution for the Mason Y's in terms of 3 parts. So the first part, this P over minus P is demonstrated to be a normally constant. So the second part is actually a propensity score, which we can get that from modeling the Mason mechanisms. And the last part, it comes from the observed part of the data. So in our model, we get the implied distribution in this form. We can see actually the variance term, the sigma t squared, is retained from the observed part, but now the mean part is decided by both the log of the missiness beta 1 and the sigma t squared. So we now have the imputation part, but we still have to figure out how to estimate the volatility. So partial Gibbs methods are becoming very popular for fitting the stochastic volatility model, and the conditional particle filter CPF and conditional particle filter with ancestor sampling CPF-AS are 2 very important ones among them. So I'm gonna give a little bit more detail about this particle filter things. So the particle filter, it recursively approximates the latent variable by particles and with some discrete probability mass or the importance weights. The conditional particle filter is based on the PF, but it now have a specific trajectory retained in the whole sampling procedure. The last month, the CPF-AS, it add another ancestor sampling step upon the CPF to address the past degeneracy problems from the CPF. So both the CPF and CPF-AS, they have advantage that the target distribution will be invariant, like no matter how many number of particles you use. So before I start to talk about the modified algorithm, I want to introduce another set of notations. So state formula is now denoted as F theta, and proposal density is R theta T, and the number of particles is N. So this modified CPF-AS algorithm is used for sample the H series and Y zero. So the first thing we need to do is initiate this algorithm by sample n particle of H1 and calculate its corresponding importance weights. So for T from 2 to N, this first thing we need to do is to check if we observe YT. If not, we have to do the imputation first. It comes from our decomposition of the likelihood. So after that, we follow the particle filter methods. We like sample n particles for HT, and given that, we need to calculate the importance weights. So if we observe YT, we can use like the available method. We use the conditional distribution for observed YT for the importance weights. But if we don't observe YT because we did the imputation, we have to account for that in the importance weights. That's why we use a different distribution here. So after we iterate for all the n HTs, we got the upper n particles, and we'll choose one from that based on our importance weights and get the estimate. So I want to briefly talk about our simulation study. We do have a couple of different settings. We have sample size at 100 and 500 represent the small sample size and large sample size. And we also have different settings for the missing parameters, the logouts of missingness. So here's the summary table for our simulation results. And I want to talk about two things from this table. First thing is we compare two methods. And another is we check the overall effect through this average mean squared error over time. So the reason why we choose to compare these two methods is because phi and sigma, they're highly correlated. And we think it might be better if we sample them jointly in terms comparing to sample them individually. So we can say if we have large sample size 500, both methods works well. But if we have small sample size 100, the second method actually are not working well and compared to the first one. And this is actually the reason why we choose to use the first method, sample jointly method, in our motivation study, because we do not have like large enough sample size to use the second one. And in terms of the overall effect, the AMSE is overall robust across the sample size. And also we found that it's increasing while we have higher odds of missing. So this is an example from our motivation study. So it's the estimated volatility for the memory happiness from the same subject I mentioned at the beginning of this talk. So in this plot, the lines, the curve are the median posterior volatility, and the dotted lines are the outcome interest. It's the time points when the subject says, "Oh, I wish I was dead at this time." So we can see the dotted lines are actually denser if we have high volatility estimated, and it's like very sparse over here, and say low is volatility. So because in the future, we want to potentially build a prediction model for this outcome of interest, the dotted lines. So we further explore their relationships. We calculated intensity function for the outcome of interest, and we calculated their correlation between this function and the estimated volatility, the original measure of happiness series, and the spline smooth series. We can say among all of these three, the volatility series actually capture the correlation very well, and it's kind of more predictable compared to the other two. So as a quick summary, we developed an imputation algorithm for the stochastic volatility model with informative missingness based on the Turkish representation and also based on our motivation study. We also extended the CPF-AS algorithm to account for the imputation method we use. And I want to mention that actually, although it's of this talk is like derived from this stochastic volatility model, but actually our imputation method can be either generalized to other state space model as long as it's suitable to use the particle Gibbs method. So currently we're working on extending the work from univariate to multivariate case, because as you may know, your effect of your mood are highly like intercorrelated with each other. So we think it might be helpful if we consider their intercorrelation as well while we estimate the stochastic volatility. And after that, we're planning to develop a method for prediction of the outcome interest. And we think it could potentially be utilized in some suicide studies as a warning system. So that's actually all from my talk today, and here's some reference. And thank you very much for listening, and I'm happy to take any questions if you have.
Awesome. Thank you so much. Do we have questions for our speaker? I have one quick question. It would just be, this model seems like it works really well for this like particular setting in this particular data set. Do you see it being able to be extended to other situations pretty readily? Mm-hmm.
Yeah, so let me go back to the settings. So like I said here, although we pick a very simple structure, but this L can be any known function. So if your study are like more complicated as compared to my like motivation study, you can choose another function like another L. And also, as I said at the end, so although it's based on this stochastic volatility model, but because it's a nonlinear state space model, and our method like based on the Toka's representation and the particle Gibbs method, they are both very general method. You can use them for any nonlinear state space model, but of course you have to derive something to make them happen, but it's actually very general method.
Thank you.
Thank you.
Okay, so on schedule now, we have a brief break, just a few minutes before our keynote speaker, Dr. Daniel Jeske. So we'll go ahead and take that break, go to the restroom, get some water, stretch your legs. I'm in California, so I'm gonna say come back at 11:30. But if you are on East Coast, or sorry, 10:30, but if you're on East Coast, it's 1:30. All right, please go take your break and we'll come back.